Welcome to This Explainer. Grab your mental lab coats because today we're taking a masterclass in the fundamental physics that govern literally everything around us. I'm talking about the invisible rules that dictate how you climb a set of stairs, all the way up to how engineers launch rockets into orbit. So let's jump right in.
To kick things off, I want you to ask yourself a seemingly obvious question. Why does climbing a staircase leave you out of breath, but just standing perfectly still on that exact same staircase doesn't? I mean, you're on the same stairs, right? Well, the true scientific answer actually lies in the fascinating relationship between three core concepts we're about to unpack.
Here's our agenda for today. We'll start with the core physics trio, break down work, energy, and power individually, hit the conservation of energy, and wrap up with some real-world physics applications.
All right, Section 1, the core physics trio, where we'll introduce work, energy, and power.
Picture this. You're lugging a heavy backpack up a flight of stairs. This everyday scenario perfectly captures how interconnected our core trio really is. Just lifting that pack against gravity, that requires what physicists call work. The internal fuel your body burns to make that happen, that's energy. And whether you sprint up those stairs or take a slow, leisurely stroll, that dictates your power. Three distinct but deeply linked ideas. Let's look closer at the first piece of the puzzle in Section 2, the physics of work, and how we move things with force. You know, the strict physics definition of work is actually pretty different from how we use the word in everyday life. You might say you worked really hard carrying a heavy bag horizontally across the room. But in physics, three strict conditions absolutely must be met. A force has to be applied, the object actually has to move, and, here's the kicker, that movement has to have a component in the exact direction of the applied force. Which leads us to this classic misconception. Let's say you're holding a 50-pound box, completely stationary. Eventually, your arms are going to shake, you'll start sweating, you will feel totally exhausted. But guess what? According to the laws of physics, you are doing zero mechanical work on that box. None. Why? Because there's no displacement. If it doesn't move, the work is mathematically zero. Physics is a pretty tough grader, huh?
Okay, moving right along to Section 3, energy, the driving force and the capacity to perform work.
So if work is the action, energy is the fuel. It's simply defined as the capacity of a system to get that work done. We measure it in a unit called joules, and it comes in tons of different flavors. Chemical energy in your breakfast, thermal energy in boiling water, electrical energy powering the device you're watching this on. And the absolute coolest part is that it's constantly shape-shifting from one type to another. But what does one single joule actually feel like? Well, to put it into perspective, 1 joule is roughly the energy it takes to lift a small apple about 1 meter up against Earth's gravity. That's it. So the next time you pick up an apple off the counter, boom, you just exerted roughly 1 joule of energy. When we talk about mechanical energy, we generally split it into two main camps. On one side, we've got kinetic energy. That's all about motion. Think of a speeding bicycle. It relies entirely on mass and speed. On the other side, there's potential energy. That's your stored energy, and it depends on position or height. Think of millions of gallons of water held back by a giant dam or a coiled spring just waiting to snap. Now let's inject time into the mix for Section 4, power, the need for speed, and how quickly work gets done. Power basically tells us how fast a task is completed. Imagine two people lifting the exact same heavy box onto a shelf. They're doing the exact same amount of work, right? But if person A does it in 5 seconds and person B takes 10 seconds, person A is generating twice the power. Power is simply the speed of doing work, and we measure it in watts. Let's tie this whole trio together with a simple analogy. Think of a system like filling up a huge water tank. The water itself, that represents your energy. The physical effort of pouring that water in represents the work. And the flow rate, how fast that water is gushing out of the pipe, represents your power. And this right here is the aha moment of the explainer, where it all clicks. It's a beautiful chain reaction. A force acts on an object, meaning work is done. That work forces an energy transfer, which causes motion. And finally, power dictates exactly how fast that entire sequence plays out. Makes total sense, right? Now that we know how these interact, let's establish the absolute rule they obey in Section 5, the conservation of energy. You've probably heard this one before, established by Hermann von Helmholtz. Energy cannot be created or destroyed. It can only be transformed from one form into another.
Guys, this isn't just a gentle suggestion. It's a fundamental, unbreakable law applied across all of physics. The universe has a strict energy budget, and it literally never changes.
So the total energy in an isolated system always stays the same. It just likes to play dress-up. Look at a simple flashlight. Chemical energy from the battery becomes electrical energy, which turns into light and heat. Or a roller coaster. It's just a constant, thrilling tug-of-war between potential and kinetic energy. The energy doesn't just vanish when the coaster hits the brakes, it transforms into heat and sound.
Finally, let's wrap up with Section 6, Real-World Physics, to see how we decode the universe using a bit of strategic math. Here's your ultimate cheat sheet. But don't worry, we aren't just memorizing formulas today. I want you to see that these actually explain how our physical reality operates. Work equals force times distance. Power equals work divided by time. But let's focus specifically on that kinetic energy formula for a second. Ke equals 1/2 mv squared.
Notice that velocity, the v, is squared. This is absolutely crucial to understand. It means even a tiny bump in speed causes a massive spike in energy. If you're riding a bike and you double your speed from 5 meters per second to 10 meters per second, your kinetic energy doesn't just double, it quadruples. It's exponential. And this mathematical reality is exactly why speeding in a car is so insanely dangerous. The energy involved scales up extremely aggressively.
As we wrap up today, I'll leave you with a quick thought experiment. Imagine pushing a locked, completely immovable car with all your might. You push until you're completely exhausted, just drenched in sweat. Have you done any work? Well, as we've learned, you certainly burned a ton of chemical energy from your own body. But because that car didn't move a single inch, in the grand realm of physics, your work is a big fat zero. Keep that in mind next time you feel like you're working hard but getting nowhere. But wait, if energy is never actually destroyed, where exactly did all your effort go? I'll let you chew on that one. Thanks for hanging out, and keep questioning the physical world around you.